A hoop of mass m, radius r, and moment of inertia m r squared rests on a rough plane inclined at an angle theta to the horizontal. It is released so that the hoop gains linear and angular acceleration by rolling without slipping down the plane. Question A. On the diagram, draw and label the forces acting on the hoop. So the first force is gravitational force or weight, and it starts at the center of mass. It's at the center of the circle and vertically downwards, and label mg or weight. And the next force, it's normal reaction, and since it's a question with respect to moments of forces or torques, it's a very important point of application of the corresponding force. So normal reaction must start at the surface and perpendicular to the surface. And the length of the component of mg perpendicular to the plane is this distance, should be approximately the same as length of this arrow, which corresponds to force m, because there is no acceleration in direction perpendicular to the plane, so forces must be balanced. And there is a frictional force which opposes motion, so it is in this direction. And again, since there is acceleration downwards, component of mg parallel the plane, this must be longer than a frictional force. So, and label this, for example, F frictional. And that's all. The next shows that the linear acceleration a of the hoop is equal to this expression. So let's choose a coordinate system. Let x be parallel the slope and downwards, and y perpendicular to the plane and in this direction, y-axis. And the second Newton's law, vector net force is equal to ma vector, and we consider this equation in projection or in components on x-axis and y-axis. On x-axis it becomes plus mg sine of theta, because component of mg parallel the plane is mg sine y sine, because it's theta, it's 90 minus theta, it's again theta, and we consider a right angle triangle, hypotenuse is mg, opposite leg is required, and opposite, it's what? It's hypotenuse times sine of theta, and minus f frictional is equal to ma. Acceleration is in this direction and component is plus a. And in projection on y-axis or in components on y-axis, it becomes n minus mg cosine of theta is equal to 0, because a is perpendicular to y-axis, so its component is equal to 0. And it's about translational motion. And what about rotational motion? A net torque or net moment of force, tau, is equal to a moment of inertia multiplied by the angular acceleration. And we consider moments which try or rotate in clockwise to be positive, in an anti-clockwise to be negative, or vice versa, it doesn't matter. And what is the moment of force or torque? It's force multiplied by the perpendicular distance or the shortest distance, and it should be considered with respect to some point. And for example, if it's some force, so a moment of force F with respect to point O, it's force F multiplied by this distance D. This D is called the lever arm, or also called pivot, or something like that. So if we consider moments about the center of the circle. Why? Because the moment of inertia, it's actually about the center of a cylinder in general, so the center of a hoop here. And with respect to point O, moment of force mg is equal to 0 because perpendicular distance from O to mg is 0, and also moment of force of n is also 0 because perpendicular distance from O to n is also 0. So there is only one non-zero moment of force. It's frictional force multiplied by perpendicular distance. It's just the radius of the circle, so just r is equal to a moment of inertia, and since we need linear acceleration, angular, it's linear divided by radius, so we can write that it's a divided by r. Or we can multiply both sides by r to get r squared here, and substituting this frictional into this, or actually we can write that frictional, it's a moment of inertia linear acceleration divided by r squared. Squared to get that mg sine of theta minus ia over r squared is equal to ma. And substituting mr squared for I, we get that it becomes mg sine of theta minus mr squared a over r squared is ma. And you can see that it becomes mg sine of theta is equal to ma plus this ma, so 2ma, m cancels, and you can see that a is g sine of theta over 2 as required. Question C. Calculate the linear acceleration when theta is 20 degrees. Just substituting 20 degrees for theta, you need just calculate this to get that it is equal to 1.68 to 3 significant figures meters per second squared. The next, state the relationship between the force of friction and the angle of incline. So from this, you can see that frictional, or actually we know, no, we should use this. So frictional, it's mg sine minus ma, and substituting the obtained expression for a, we get that it becomes mg sine theta minus m g sine theta over 2, and you can see that it becomes just mg sine of theta over 2. So it's D is B. Then question E, the angle of incline is slowly increases from 0. Determine the angle in terms of the coefficient of friction at which the hoop will begin to slip. So we know that frictional force is mu n, coefficient of friction multiplied by the normal reaction, and normal reaction from this you can see that it's mg cosine, so it becomes mu mg cosine of theta. And from the other hand, frictional is this, it's mg sine of theta over 2. So mu mg cosine is equal to mg sine over 2. And you can see that mg cancels, multiplying by 2 we get, and dividing by cosine of theta we get that tangent of theta is equal to 2 times mu. And it's the required expression. Actually, it's not required, but theta is what arctangent or inverse tangent of 2 mu, but it's acceptable. And what does it mean? If theta is greater than 2 mu, there will be slipping. Or in general, we can write that mu must be greater or equal than tangent of theta over 2, so that it will not be slipping. And if theta is not small enough, and from the other hand mu will not be large enough to keep it rolling without slipping. But inequality is not required here, so it's the required relationship. And that's also for this question.